solenoid is a copper winding which is wound on an insulating base. Usually it will be a hollow base, create the magnetic field in the solenoid. So what we usually have here is, it will be an insulating base. So it will be mostly a cylindrical base. It will be like this, and on that, on the top of that, we are going to have the copper wire wound like this. So I had shown you this diagram. Again, I am going to draw it in a rough way. So this is my copper wire wound on the top of the insulating base. So this is the insulating base, and this is the copper wire that is going to come out of the board, and from the bottom the current is going into the board. So the magnetic field is going to be produced in this way. On the top it will be anti-clockwise, and on the bottom it will be clockwise. So this will be the formation of magnetic field. Now if we look into this magnetic field, they will add up, and this was anti-clockwise here, so it was going like this on the outside, and it was going towards right on the inside. Now if I want to join all these magnetic fields, because ultimately they will be joining together, and here it will be the formation of magnetic field is going to be like this, and on the top if I look here, the magnetic field is going to go in this way, and from this side the magnetic field is going to be going in this way. So this will be the formation of magnetic field. Similarly, I can draw the magnetic field for the bottom portion. So if I join all of them, it is going to be something like this. The magnetic field is going to come out like this, and it is going to go past. Like cut a cross section from this one, then if I take the magnetic field, it is going to be like this, because the current is coming out, so it will be going in this way. Similarly for this one. Similarly for this one. Again for this one, since the current is going to be coming out and it is going to be going like this, the magnetic field is going to be like this. Now if all the magnetic fields join together, it will be something like this. This will be facing towards left, and this will be facing towards right. Similarly for the bottom portion, if I join all of them, then it's going to be, all of them are going towards right and it's going towards left. So if I see the magnetic field lines will be coming out from here, so I'm going to see a north pole here, and the magnetic field lines will be going inside. So this here I'm going to see a south pole. So that is how a solenoid is going to produce the magnetic. So one solenoid can have thousands of windings over it. So when we have that thousands of windings wound onto that insulating base, what we have here is going to be, it is going to be looking like a cylindrical sheet, because there will be so many windings which are very closely arranged. What we are going to see is only a sheet of metal. What we are going to see, we are going to see only the wires on the top as well as only the wires on the bottom, what we are going to see. Now if I look into this one, if this is my insulating base, if I say that, as I had said in the last class, the radius will be very small compared to the length of the solenoid, then it is going to be, what we are going to see here is, this magnetic field is going to get stretched to a very wide range, and inside the magnetic field is going to get concentrated, and when we see on the outside, the magnetic field is going to be distributed over a large volume. And when that happens, what we are going to see here is, the magnetic field on the outside of the solenoid will be negligible, and the magnetic field in the center of the solenoid will be very strong. Look for that one. This I have shown, there are hundreds of windings on this solenoid. Then if I want to find the magnetic field of this solenoid, then I cannot find it directly from the equation or directly from this by applying Biot-Savart's law onto this winding. On this it is okay because we can count the number of windings and we can apply the equation of Biot-Savart law and we can get the magnetic field. But for this case, what we have is we have got n number of windings per unit length. So when we have n number of windings per unit length means if I want the total number of windings of this one, let us say the length is L, then if I want the number of windings of this solenoid, then it will be n times of L. So many windings will be there on that solenoid. Now if I want to find the exact value of the magnetic field produced by this solenoid on the inside, then we need to apply the Ampere's circuital law. We need a loop. Inside that loop, we need some number of windings passing through that one. So that what is the Ampere's circuital law? It says V dot dl is equal to mu naught into I enclosed. So it will be the surface integral of this thing. So this is the statement of the Ampere's circuital law. So we need a loop across which we are going to find the magnetic field due to this solenoid. So for simplicity, we will take a rectangular shaped loop, and that loop is going to serve as our enclosing loop across which we can find the magnetic field. Now for our understanding, let us take A, B, C and D. Now there are 4 parts of this loop and we want to calculate the magnetic field which is going to be present inside that loop due to the number of windings which are present inside that loop. Now for simplicity, let's take this as H, the number of windings present only within that length of H. So in that case it will be NH. Now each winding of that inside this loop, it is going to carry a current I. So it will be NH into I. Now I want to apply the Ampere's circuital law to that loop. As I had given the explanation just few minutes ago, on the outside the magnetic field is going to be negligible. That means the portion CD will have a very negligible magnetic field. Similarly, if we look into the sides AD and BC, those are perpendicular to the solenoid. So that part, those parts also will not be contributing to the magnetic field. So there is no magnetic field on AD, there is no magnetic field on BC, and also the CD part we are going to have a negligible amount of magnetic field. Now where the magnetic field is going to be present? The magnetic field is going to be present only in the side AB of the solenoid. Now if I want to calculate, so I will apply the B into dl equals, and this will be mu naught NH into I. N into H is the number of windings which are present inside that length of H, and I is the current carried by each winding, and mu naught is the constant which we need. Now what is this integration of dl? It is going to be this length, and this length AB is equal to H. So B into H will be equal to mu naught NH I enclosed, or I can take that just as I because I have already taken that NH. Now H on right hand side and left hand side will cancel. What is left is B is equal to mu naught NI. That is the equation for the magnetic field produced by a long solenoid. This is the toroid. Now we want to find the magnetic field which is going to be produced by a toroid. Okay, this is the physical structure and there will be windings on this wire. So I'm going to show the cross-sectional cuts of the windings. So there will be wire which is going to be cut and we are going to see only the tips of the wires which are on the top of the toroid as well as on the bottom end of the toroid. So this is the same toroid. What we have done is we have cut this in this way, and what we are going to see, we are going to see the tips of the top wires and the tips of the bottom wires, what is being shown here. Now I want 3 more circles. I have shown 2 circles. Now there will be 3 circles. I am going to take them as dotted circles. One is going to be on the interior, one is going to be on the exterior, and one is going to be passing in between the tips of the wires. So totally we need 5 circles. Now if let us say this is the center, this I can take it as radius R1. The second one which is at the center, this I can take it as radius R2, and the third one which is the outermost, I can take the radius as R3. Let us take the center as O. So I have a center, I have got 3 imaginary circles going to be my Amperian loops, around which I am going to calculate the magnetic field produced by this toroid. So how we are going to do that? Let us say for the first circle, for the loop with radius R1. R1 means it is the innermost circle, it is the smallest circle what we have. Now what our Ampere's circuital law says is the integral of magnetic field across a loop should be equal to mu naught into I. Now if this is my loop, this with radius R1, if this is my loop, is it enclosing any current element inside that one? No. The current element is there, but it is on the outside, as well as these current elements are also outside the radius R1. So there is no current element enclosed by the loop of radius R1. That means this I is 0. There is no current element, means there is no current is enclosed by that radius R1. So what I am going to get here is for loop 1. Let us say this is the loop of radius R1. B dot dl is equal to 0, which implies the magnetic field is going to be 0. So there is no magnetic field present in the central area of a toroid. So that is the first thing. Now let's go to the outermost, because that there also we are going to get a 0 for loop 3 with radius R3. Let us take this outermost circle which has got a radius of R3. Now if you look here, let us say the current is coming out from here and is going in from this side. Same thing is true for all. This is going to be coming out, this is going to be going in, coming out, going in, coming out, going in. It is going to be applied for all the tips of this diagram. So each tip is going to be contributing to the magnetic field. One side is going to be contributing a clockwise magnetic field, the other side is going to be contributing to the opposing magnetic field. So whatever the field is produced by one side, the other side is going to cancel that magnetic field. So the current coming out of the plane is equal to the current going into the plane contained by the loop of radius R3. So equal and opposite currents will produce equal and opposite magnetic fields. So again the B, that is the magnetic field, is going to be having a zero current. So again the magnetic field is going to become zero with radius R2. This is my loop, and in this loop we have only the tips which are through which the current is only going inside the paper, inside the plane. Nothing is coming out. So I will have some number of current, some current enclosed by this loop with radius R2. So what I am going to have is, I am going to have the integration V dot dl equals to mu naught I. So that is my Ampere's circuital law, and here it is applicable as there is some number of elements and all of the elements are carrying the current in the same direction, that is going into the plane of the paper or going into the plane of the board. Then I can have this current as n times of I. So this I is going to become n times of I, because there are n number of tips which are going to be contained in this loop with radius R2. So I have got my n times of I, and there will be mu naught, which is the constant, and there is d, and an integration will be applied to dl, and that integration of that dl is going to be the circumference of this circle with radius R2. So it is going to be 2 pi R2. Now, what is the total number of turns? If this thing was a straight solenoid, one single straight solenoid is what it is going to be? It is going to have some number of windings which are going to be extending for some length. So what is going to be having here is 2 pi R2 into n. This is going to be the length of the solenoid. Radius ಇದು straight ಮಾಡಿದ್ರೆ it is going to be some straight line, and around which we are having the magnetic field. So that n, that capital N, can be replaced by this one, and if I replace this thing here in this equation, it implies B into 2 pi R2 equals mu naught, n will be replaced by this term 2 pi R2 into n into I. So this 2 pi R2 gets cancelled. B equal to mu naught n into I. What is this n? N is the number of windings per unit length of this solenoid, or in this case it will be a toroid.